Last class, we've learned all of the theorems that we need to factor polynomials of higher degree. So we went through remainder theorem and factor theorem, which are basically the same theorem, right? You're checking a division by a polynomial x minus a. So we're only doing these types of divisions by this polynomial where a is just an integer. And if you plug it into P of A and you make that calculation, the remainder theorem says you get a remainder after that calculation. The factor theorem says that if the remainder is 0, your x minus a binomial is a factor. That means you have no remainder, right? So plus 0. And the third theorem we learned was the one that tells us which ones are the factors. And that's the one that we're going to use to start the process of factoring higher degree polynomials. We're going to look at the free term, which is -12 or 12. And we start by listing the factors, the integer factors of 12, or the numbers that divide 12. Positive -1, positive -2, positive -3, positive -4, dot. I don't waste my time more than 3 or 4 in the list because I'm hoping to find the first one pretty fast, and then continue on. Okay, so then I go down the list one by one. P of 1. 1 to the 4 plus 1 cubed minus 13, 1 squared minus 25 times 1 minus 12. Try not to copy from the board because that's gonna be always like this. Try to hear what I do and try to write from listening or kind of picking up what we're doing and just looking at your own paper and just checking to see the board matches your own work. So plugging in 1, right, into the equation, and we're just calculating, right? Okay, so we get 1 from here, plus 1, minus 13, minus 25, minus 12. You can eyeball it before you plug it in. Is that going to give us 0? No, because so many negatives there, right, that are big. Not 0. Go to the next one. Clear for everyone? So far, so good, right? So now the next one, the -1. -1 to the 4 plus -1 cubed, and keep going. Just plug in negatives now everywhere you see an x into your polynomial. Every time you raise a negative number to an even exponent, your answer is going to be positive number. When you raise a negative number to an odd exponent, then your answer will have a negative in front of it, okay? So -1 to the 4 is going to be +1. -1 cubed is going to be -1. Now this one, I'm going to do one calculation in my head and then the second one also in my head and put the answer down, right? So -1 square has to be done first. That's +1 times 13 negative. It's going to give me a -13. -1 times -25 is +25 minus 12. Now I see 26 for the positive. -25, -1. That looks like I have a factor here, right? The first one equals 0. If you're not certain, if the numbers are really close by, just take your calculator. I'm going to let you use the calculator and check it out, okay? Just show your work because in calculus, you're not going to be allowed to use the calculator. And the more mental math you practice right now, the better it's going to be for you, okay? So let's say that x plus 1, so opposite, is going to be a factor. We're going to put it into synthetic division. So 1, 1, -13, -25, -12, -1, and get our quotient. -1 times 1, -1, 0, 0, -13, 13, -12, 12, 0. So this is no x, that's a x to the 1, that's x squared, that's x cubed. Now, if you want, you can write so far. I only write so far in the notes, so you understand that after each factorization, you will have a multiplication of two polynomials, right? So this p of x so far would look like that. X plus 1, our factor, times this quotient with no remainder. So basically, we write a statement, right, for our polynomials. One of those statements we have learned. So x cubed minus 13x minus 12 is my quotient was. I left out the 0x squared. I only need that 0x squared for a division, right? The placeholder for the x squared term. So far I have done this factorization. It's not complete. Okay, I still have to check to see if I find more factors for this quotient that I just found, right? Make sense? Okay, so now what I like to do, I always like to check again, okay? You don't have to, you can go down the list if you want, just in case I get something that's squared or cubed, right? I can find it right away. So I check again, p of -1 into my quotient. So -1 cubed minus 13, -1 minus 12. That's -1, 13 minus 12. Equals 0, right? You see, it appeared again. So we're going to have an x plus 1 factor again. So then we're going to go to synthetic division. 1, 0, -13, -12, and -1. And get a quadratic quotient, right? Because now we have a cubic divided by a linear. It's going to give us a quadratic. -1 times 1 is -1. Add vertically, -1. 2, add vertically. Not 2, 1. I was like, where is my 12? -1 times -1 is 1. Add vertically, -12, 12, 0. No x, x to the 1, x squared. So far, so good? Okay, now I have these two and this one as my factor. This is also not factor complete because I have to see if this quadratic trinomial factors further into two linear binomials, right? So how do I check that? How do I check x squared minus x minus 12? Well, since I don't have anything in front of x, basically having 1 there, I can use the shorter version of factoring only by checking two factors of -12 of the free term that add up the middle term. So what two factors of -12 add up to -1? -4 and 3, right? So that means we go straight to x minus 4, x plus 3. But this method only works when you have here 1. Anything else different than 1, you have to multiply. Even if it's -1 there, that's still not 1, right? -1 is not the same number as +1, right? So then you still have to go and do the longer version. The first one we learned, it's called factoring by grouping. So now what do we have our p of x? Finally, because we completed the factorization. We had these two, so x plus 1 times x plus 1, factors multiply. That means we can write it as x plus 1 squared. And then x plus 3, x minus 4. It doesn't matter in which order. That's your complete factorization. Now, if this question were to be an equation, if this question said solve x to the 4 plus x cubed minus 13x squared minus 25x minus 12 equals 0, the process is exactly the same up to here. So you have to go through all this to factor it. So you would get to x plus 1 squared, x plus 3, x minus 4 equals 0. Okay, and then you take each bracket one by one and solve for x in them. That's called splitting and solving. So you split it into the first one, x plus 1 equals 0, x equals -1. And you would get your first solution. It just happened that it happens twice, okay? We call it multiplicity of 2, okay? Because it comes from this 2 right here. And then you take the next one, x plus 3 equals 0. You get x equals -3. And then you get x minus 4 equals 0, x equals 4. Okay? So that's all we learned last class, basically, all in one question, the continuation I have just done, right? So we started last class learning the theorems, because without them, we wouldn't be able to factor, right? And then we practiced them through the factoring, of polynomials completely, or just finding one or two factors. And then once we know how to factor, we can apply that skill of factoring into solving higher degree polynomial equations, okay? And then how do you get it? Well, you get to the factored form, and then you just split and solve each of the brackets. Questions?
Indicator to know when to let stop factor.
When you cannot factor further. So your goal with all of the factoring tools you have is to get to a quadratic, right? And then if you got to a quadratic, if it's not factorable, you'll find that none of the factor pairs will work, right? Let's say you get to a cubic that's not factorable. How can you determine if that is not a factorable cubic? Well, you have to go through all of these factors using the factor theorem. And if you completed the list and none of them gave you a remainder of 0, obviously there's no integer factor for that factorization. Okay, but you do have to then check all of the list. You can't say, oh, there's no factors because I got tired of checking. You have to check it all. Yes. You don't have to ask. You can always just go.
So pretty much you've got then sit down step by step, lowering the exponent value. And then eventually, hopefully get to a point where your first x value equals 1. And then you can change it to the easier method and the less painful method. Yes,
that's right. Now, I'll give you a sort of a shortcut to this method, because when you have to solve a, let's say, a higher degree equation that's degree 5, it's going to take you a long time. A lot of the times we can just basically skip these parts. You can just go straight if you prefer. If you don't want to go through checking factors through factor theorems, you can also check factors to synthetic division. So basically, just go and do synthetic division by 1. Don't get 0, not a factor. And then go to the synthetic division for -1, get a 0. Oh, here's my factor. And you're going to have basically a bunch of boxes only with synthetic division until you get to the quadratic. Okay? And you can do that too. So you're not using these, just straight these. How about we go through 2.5, and I'll show you how to use that method too. Okay? And then you will see if you want to use it or not. 2.5, I'm not going to do A because that's already factored. We're splitting and solving there, and we're getting our solutions, okay? But let's do the negative x4 and all of that. Okay, I'll show you that. Now, the first thing I'm noticing when I'm solving an equation, so notice you have to solve the equation. That means you have to get it to a form like part A in factored form, so you can then split and solve. Now, I'm noticing because of that reason that I don't have equal to 0. Don't go ahead and factor without moving everything to the left and have it equal to 0. The idea of splitting and solving doesn't work if you don't have equal 0. It only is working because you can let every single one of those brackets be 0, and then that being 0 cancels everything else because you're multiplying by 0, right? That's why it works. Okay, and then you take it to the next one and the next one, right? So we have to make sure the splitting and solving works by moving everything on the left and then make it equal to 0. If you want a separate sheet of paper, there's a box in this room that says scrap paper. It has sheets of white paper on one side from the printer. So a 5x squared plus 36x plus 31 plus 5, so plus 36. Okay, and then we start the same way. We need a factors where to check. So first we do factors of 36. Plus minus 1, plus minus 2, plus minus 3, plus minus 4. Da, da, da. Now, in my solutions, I factor out the negative from the beginning, and you can do so. I like that. I like to work always with the first coefficient being a positive number. So I always factor out the negative. So I'll give you an alternate solution this time. You're already doing it differently to begin with. Why not see that you can do it another way? So let's go down the list. But instead of checking using factor theorem, let's do just synthetic division so you can see how that looks like, okay? So synthetic division straight, and I'm going down this list. So I'm checking 1 first. Yeah. We move it on the other side. We added 5 to both sides so we can have equal 0 here. Yeah. We always do that when you have equals a number. So just check 1 with -1, -4, 5, 36, and 36 again. -1 times 1 is -1, -5, -5, 0, 1. What's going on? 0, not 1, and then 36. 36, 72. Not a factor. Let's double check our signs. 36, and then -1, -5, -5, 0, 0, 36. Yeah, agreed? Yeah, so we have a remainder. This is not a factor, okay? That's how you can check one by one with factor, with the synthetic division. We go to the next one. We're gonna check -1. -1, drop it. -1, negative, +1, -3, 3, and then 8, -8, 28, -28, not a factor. So you got -28, so that's 8. Agreed? Let's check our signs again. Negative, negative, positive, 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 negative, positive, negative, positive, negative, positive, negative, positive. Agreed? Okay. We go to number 2 now in the list. -2, -6, -12, and that's -7, -14. That's 22. And 44. We have a remainder of 70, 80. So it doesn't work. Check -2. Two, -2, 4, 9, -18, 18, -36, 0. Check our signs. Looks like it's correct. Agreed? Okay, so our first factor is x, what? Plus 2, you got it. And then we have here nothing, and x squared, x cubed. So we're still not into the x squared yet, right? Because we only divided our quartic by a linear and we got a cubic, right? So we continue on. We can check again -2 because we might get something with the multiplicity. -1, -2 from here. 9 and 18. And we check again -2. Zero, 0, -18. There it is, one more. Agreed? Okay, so we got the 0 remainder here. So we got another factor of x plus 2. Now this one, no x squared. This is a quadratic, right? So we have -x squared plus 9. Or you can write a 0 too if you want to use that method. This one actually I could factor it a little bit different, but I don't want to overwhelm you just yet with that method. So -x squared plus 0x plus 9. Now here, notice how you have a negative in front here, right? So you want to make sure that you understand you can't go to the direct method of factoring straight to something like that because of this -1 here, right? So you have to use the longer method to get to your factor. So you have to times these two, -1 times 9 first is -9. What are two factors of -9 that add up to 0? -3 and 3, right? And then you split up with x's. -x squared minus 3x plus 3x plus 9, -x plus 3 plus 3x plus 3. And then x plus 3 is the common factor, -x plus 3. And I can also factor out this negative out in front. So we have a -1. X plus 3 stays, but I'm taking out the -1 from both of these terms. So I would get an x there and -3. And now we're going to put it all together. So we have these factors. This is a factor. And that's a factor. So what is my final equation looking like before splitting and solving, right? I have x plus 2 appearing twice, right? We have x plus 2 squared. I have an x plus 3, and I have an x minus 3 equals 0 with a negative in front. Clear? Now what do you do to solve for x? To solve the equation, once you have it in factored form? Any ideas? What do we do to get the x's now? equal them to zero. Every single bracket must be equal to 0, either on paper or in your head, because now it starts to get clear what x is once you do a few practice questions, right? So what is x from here? -2, right? If you put there -2 plus 2, you get 0 there, right? What's going to be x in the second bracket? -3. What's the x in the third bracket? 3. And this one has a multiplicity of 2.
X squared plus 9, or you could just keep the difference of square.
That's right. That's the method that I didn't want to say yet. Yeah. Mhm.
Matter where you put it, as long as it's like close to it.
Yeah, it doesn't matter. Just you want to mention it's a multiple. It doesn't matter for the equation, but it's gonna matter with lesson 3 for functions. Being a multiplicity that's even or odd will be important for the graph of the polynomial function. Okay, so that's basically your quiz today. Okay, it's just gonna be lengthy in terms of your work checking, but it's not extremely difficult, right? In terms of the steps, I hope, right? You just need to know how to factor, okay? Get your factors, simmer it down until you get to a quadratic, okay? If you're having a quadratic, try to factor it. If it's not factorable, then you have to use the quadratic formula, okay? When you're solving an equation, because, you know, factoring is just one way of getting your solutions. The easier way, because it's factorable. But if you don't have factors that are integers, then you will have to go to quadratic formula. Okay. A little bit, feeling a little bit better? A little bit? Okay. But yes, you're definitely right. If you're feeling like you're rushed, fast paced, you're right. It is fast paced. It is only twice a week. It is 3.5 hours, so even more than university courses, because they're like, what, 1 hour still? They are, right? 1 hour. 50 minutes? Oh my goodness, right? So definitely a way different field than everything else probably that you've ever done, right? It's designed like this because a high school credit has to have a certain amount of hours, direct hours, teacher, student, you know? So the only way you get that is with this amount of hours. Yeah. I feel for you, but at the end of the day, you will get your credit, right? Only into 29 days, right? So just stay with it and you'll be okay. That's right, yeah. It's faster. It's faster and it's condensed and it's less classes. Exactly. And it's also a lot of the things that I'm teaching you is from grade 11 too. Like all of the factoring of quadratics, you should already know that, right? From grade 11. So either I just assume, hey, you know this and go straight to higher factorization and don't care that you don't know it, right? Or I go over it and stop with you and explain to you which we have to do in our bed. Especially when we don't ask students to have a prerequisite of grade 11, we get a lot of things that don't have it and just try to get to university faster, right, without the grade 11 credit. Okay, so I'm glad that you're starting to notice all these things and then you're starting to manage your time accordingly, okay? And put in as much practice as you can, but not all at once. Just try to split it up into groups of, I don't know, an hour, you know, if you can. Don't do 3 hours at once, because then you're going to be dreaming about X's. Okay. Moving on to polynomial functions. We're going into some definitions for functions. One of the central ideas of mathematics, the modern mathematics, is the idea of function. A function is a special kind of relationship between two sets of objects where we have a relationship that's directed from one object in the first set. This first set is called the domain. towards another object in the second set, and the second set is called the range. And how do we know how to go from one to the other one? We're gonna have a rule that's gonna tell us how to get from one object to another, a map. And the map is gonna be a certain equation. It's gonna tell you how to calculate something with a number to get to another number in the other set. So here's a couple of descriptions here, how the rule can look like. So I can say double the input, so double the number 2, okay, and then add 1, right? So I can choose something, I can manipulate it with a certain operation, and then I can get to another thing. And then instead of writing with words, because mathematics is, I think, the best example of writing something with at least words you can possible, right? So everything in terms of equations or simplified. Instead of writing that, double the input, add 1, I can just say 2 times x plus 1, okay? Means exactly the same thing. X will be the input, okay? And then y, what we're getting after that calculation, that's sometimes called the output of the function. So input, and the y would be the output. Now, if you start choosing a series of inputs and you're gonna get a series of outputs, you always will have these pairs that you're creating, the input you chose and the output you solved, you calculated. We call these ordered pairs, and they're gonna look like this, x, y. And it's called ordered because it's always in exactly this order. X always has to be first in this pair, and y always has to be second. X is the input, y is the output. X is from the domain, the first set, and then y is from the range, the second set. And these series of pairs, if we put them into an XY system of axes, it will give us the graphical look of our function. Okay, it'll be dots, it'll be points on the graph. We'll be able to unite them most of the times. Then we're going to get a line or a curve that's going to give us the graph of the function. Here's another look at the mapping of domain range relationships. This is the domain. That's the range. The rule is 2x plus 1. So if I take 1 from the domain, if I do 2 times 1 plus 1, I get 3. So it takes me to something in the range. If I choose 4, I would say 2 times 4 plus 1, I will get to 8. So I'll have another relationship. So I will have a series of pairs, 1, 3, 2, 5, 4, 8. All of these are points on the graph of the function. Do you remember this? Grade 9? 10? Even earlier on, because you do mapping of points even in middle school. Okay. I'm gonna talk about this graph here in function equations and tables of values. A function equation is a mathematical expression that describes what operations, and I'm referring to mathematical operations, not medical operations, are applied to the elements of the domain to obtain the elements of the range. So back to our 2x plus 1, we are told that we are choosing the number x, that we're going to multiply by 2 and add 1 to obtain a y. If we choose x equals to 1, 2 times 1 plus 1 equals 3. We have the order paired. If we choose -1, it's going to be again the operation 2 times -1 plus 1 equals -1. So we get another pair and so forth. Instead of writing it like this, we usually organize these calculations in a table of values. So we just do like that, X, Y. Mine, it looks a little bit nicer because it's already there for you. But usually just like a T like this, X, Y. And under the X's, you're just making choices for possible X's. Okay, so then usually I always choose nice numbers like 0, 1, something that I can calculate really easily with, okay? If you have to do your own work. In other situations, we have weights to determine which choices are the best choices for our particular questions. So if I choose 3, then I could do 2 times 3 plus 1 based on the rule. So I would get 7. So I would get a point that looks like that, 3, 7. This is called a table of values. Now, for the names of these function equations, we usually choose lowercase letters. And I think everybody knows this, but just in case you've forgotten, F, J, H, every one of these letters are okay for naming your functions. Usually we use F. You've seen this notation up to now, F of X, okay? That's the function named F. And it says of X because X is the input. So it describes which one is the domain variable and which one will be the range. So instead of writing y equals 2x plus 1, a lot of the times we prefer to write it like this notation, f of x equals 2x plus 1. And notice the relationship. Notice how y is replaced with the notation f of x, because this notation names the function as well. F of x is read as f of. It's not f times x, okay? It's just notation. Now let's define polynomial functions. A polynomial function will look just like our polynomial expression, but you have to equal it to y to show that it is defining how to find your pairs of numbers. Okay, you put something into x, find the y. So it's always a pair of numbers that will give you a point. So notice how y is not 0, okay? If it's 0, then it's an equation, okay? If it's y, then you have a bunch of relationships that you can build, a bunch of values you can create. All of these things we've talked about already. The exponents are whole numbers, and if they're written in descending order, we call this the general form. So usually when we define it, we always write it in descending order of exponents. We also name the functions by the highest exponent. So if we have a function of degree 1 is from the highest exponent of our x's. The coefficients, all these a's, these are going to be numbers, are going to be real numbers. The leading coefficient cannot be 0 because otherwise I'm not talking about the same type of function. The last number there that doesn't have an x is called the constant term or the free term. That's going to mean something for our functions later on. Any questions for the polynomial function definition? Here's an example. Y equals 4x cubed minus 3x plus 5. Another example. G of x equals negative 2x to the 4 plus x cubed minus 4x squared plus 3. I'm just coming up with some x's there, okay? But basically, again, you have to have your polynomial expression the same way we have seen them up to now all the time, okay? and then it's equaling either y notation or the f of x, g of x, h of x notation. And then you have now a function description. Okay, now the domain. The domain is talking about all of the possible numbers that you can plug into x. For polynomial function, you can put anything into x and do the squaring and the cubic, right? So any number you can imagine is what kind of number? Any number that makes up the number line is what kind of number? A real number. So the domain of the function we say belongs to the real number is x belongs to R. This notation means x is an element of the real number. So is an element of is this sign right there. Now, the range of polynomial functions is a little bit different depending if you're talking about a degree 1 or if you're talking about degree 3, for example, or better said, degree 2 or 4. So if it's even or odd. So the range of polynomial function is going to be always the real numbers for odd degrees. So y, which is the range variable, is an element of the real numbers. That's for odd degrees like linear, cubic, quintic, okay? And for even degrees like quadratics or quartics, quadratics you've seen, they're parabolas that like that or like that, right? That's grade 11 stuff. You either have something that's bigger than a value of y or something that's smaller than a value of y. So it's a bit more limited in terms of what values you can have for your range. So we can write that like this: y is bigger and equal to a number, or y is smaller and equal to a certain number. And then this number would be a minimum. This number would be a maximum value. How are you doing? Hanging in there? Good, good. Let's visualize the graph. So we know that when we do a table of values, we get all those pairs that will give us the graphical representation of the function. Polynomial functions of degree from, let's see how, what I would say here, from 1 to degree 2 or more are graphically represented by curves with hills and valleys. Now, I left out degree 1. Why? What do you think is the graph of degree 1 functions? A straight line. So with the exception of degree 1 or a constant function, which is just going to give you a horizontal line. So for example, y equals 3 will give you a graph like that through 3, horizontal line through 3. And if you have y equals 3x plus 1, it will give you a straight line that looks something like that, okay? Check the airflow. So what am I, like an airflow checker? I don't know. I think that's in there something. It's gonna disappear right away. I don't know. No. Get out of there. So for the function 2x plus 1, every xy pair found with the table value is a point on the Cartesian plane. Cartesian plane is a fancy way of saying the XY system after a mathematician slash philosopher Rene Descartes. So when these points are plotted in the Cartesian plane, we will see the graph of the function. Linear functions and quadratic functions you have done before. These are types of polynomial functions. On the next page, we will review Cartesian plane plotting of points by graphing some of these functions. I think linears I only have here. So here's a bit of review. Graph the following functions, state, domain, and range. For linear functions, all you need to do is figure out 2 points that belong to the function, because we can draw a line by having 2 points only. You can have more if you want, but it won't matter because your line will go through all of those possible points. The first function, h of x equals negative 2x minus 3. We're going to do our table of values, x, y, or x. You can also write, instead of y, you can write h of x. And then here in the first column, you make choices. You remember we talked about domain values can be any real number for the polynomial function. That means I can choose any number I want and work with it to get a number from the range, right? So these are all your choices. And I always choose something easy to work with, right? So 0, my first choice is always 0. And I can do negative 2 times 0 minus 3, and I get negative 3. My first pair is 0, negative 3. And what would be your second choice for a calculation? 1, yeah. Negative 2 times 1 minus 3, that's negative 5. The point 0, negative 3 is a special point. It's going to land on the y-axis. So we call this point the y-intercept. It's going to be right there. The other point, 1, negative 5, it's going to be at the crossover of a vertical horizontal line through those imaginary lines. So for example, you think about 1 here, negative 5, through 1 a vertical line to negative 5 a horizontal line. And where they meet at the corner, that's where your point is. And there's our line. Grab your ruler. Or, I don't know, a credit card. I'll check the airflow again. There you go. It's for the 1, negative 5. Yeah.
That's your y value.
That's a y value, because you don't, x is here 0, y is negative 3, so they meet right there.
Right.
And for 1 is 1 here, and they just meet at that corner right there. And then once you have 2 points, that's all you need. Because even if you choose the other points, they're just going to be somewhere along this line we just drew. We have 2 points that we came up with, but other people can come up with other points on the same line. It's still going to be exactly in the same location. Okay. And the other one? 2b's there. That's my error there. K of x equals 1/3 x minus 1. So table of values, because it's still a linear function. And then I always choose 0. That's 0 is always a good choice because it cancels the first or all of the terms that have x's in them. Like my first point, 0, -1. And the next choice has to be clever because you're working with fractions. So depending on your choice, you're gonna have a harder or an easier time with your calculation. So if you choose 1, for example, you have to work with 1/3 -1, and then you're gonna get a fraction, and then you have to plot fraction values on your graph. So not nice locations in your Cartesian plane. So what would you choose for the next choice of x? 3. So any multiple of 3 would work. The lowest one will give you a lower value, obviously, but yes, multiples of 3, 3, 6, 9, and all that. Yes. So 3 I would choose because look what happens. 1/3 times 3, right? You get a whole number 1. And then subtract 1. So we get 1 minus 1 equals 0. 3 and 0 is our point. So we have a point at -1 on the y-axis. We have a point at 3 on the x-axis. They're both intercept. This is the y-intercept. That's an x-intercept. It's just a name for them. -1 right here. And 3, 0 is right there. 2 points, you can draw a line. Denominator.
Yeah.
So if you work with 1/7, then you're gonna choose here multiples of 7 because of the denominator. It will just cancel it out nicely, you know. 1/5, you're gonna choose 5, 10, and so forth, okay? Not saying that you cannot choose other numbers because the domain of the function is all real numbers. So you can go ahead and choose anything you want, but it's not gonna give you a nice integer to work with. It's gonna give you a fraction that you have to work with. Okay, so let's talk about these special points called the intercept and give you some review notes for them. X-intercepts, sometimes they're called the zeros of a function, are the points of the form x0, where x is just a number, a real number. Visually, where were the x-intercepts located on the graph? On the x-axis, right? So visually, the x-intercepts are where the graph touches or crosses the x-axis. So on the x-axis, okay? Depending on the function, there can be none, one, or more x-intercepts. So for example, I'm going to use the quadratic function to show you an example where a quadratic function has no x-intercept, one x-intercept, or two x-intercepts. So you can see there's different situations for different functions. So when we have none, the quadratic function parabola will look like that, either like upwards, so you can see it doesn't touch the x-axis, right? So no x-intercept, no zeros. If it has 1, the vertex is going to be touching the x-axis, so that's going to be the x-intercept right there at the vertex. Matthew, you good? You copying this? And then for 2 zeros or 2 x-intercepts, you're gonna have a parabola that crosses in 2 locations, right here and right there. And similarly, it's gonna be for all the other functions except for the linear function. The y-intercept is a point with the form 0y. Again, y is just a number. There's only one y-intercept. You cannot have multiples, just one for a function. Same thing visually, the y-intercept will be similarly crossing or touching the y-axis. The other way around, in rare example, it flipped them. Now we're gonna do some examples. State the intercepts of the given function. So you have the given function graphically here. We just need the intercepts. The y-intercept is at 0, 3. We can state it as a point, 0, 3, or we can just say y-intercept at 3, because when you say y-intercept, it's understood. You're talking about the point where the x-coordinate is 0. X-intercept is at -3, 0, or we can say at -3. Now, can you find the x and y intercept algebraically? Yes. For the function f of x equals -3x plus 2, find the x and the y intercepts algebraically. So I'm going to split this space into 2. So I have one space for the y-intercept calculation and one space for the x-intercept calculation. So let's start with the y-intercept because it's the one that's easier to find. When we are calculating the y-intercept, what we do is remember that a y-intercept has the form 0, and y is going to be the one that we're going to find, the number, right? Meaning we have to let x equal to 0, because that's what it means. If I have to find a point that has x equal to 0, I can just assume it's going to be equal to 0, right? The point that I'm finding. So in the equation, if I let the x equal to 0, all I have to do is replace the x with 0 and calculate the y, right? So calculate y. So that's basically what I memorized for myself when I'm calculating y-intercept. I'm saying in my head, let x equal 0, calculate y. And then I go ahead and do what I just say I'm going to do. I'm saying y equals -3, 0 plus 2 equals 2. So I've calculated the y-intercept to be 2. The y-intercept is 2 or 0, 2. For the polynomial functions, the y-intercept is always going to be the free term, notice, right? Because if you let x equal to 0, it will always cancel all of your x terms. We'll talk about that a little bit later. Now for the x-intercepts, you're going to remember that the points that are x-intercepts are the points that have an x number there, and then the y has to equal to 0. And what I say to myself is I'm gonna have to let y equal to 0 and solve for x. Now, when you're calculating x-intercepts, you're not just calculating everything on the right-hand side of the equal, you're actually gonna end up with an equation, okay? You have to work backwards to find out those x's. So I'm doing what I said I'm gonna do. I'm gonna put negative 3x plus 2, let that equal to 0. Negative 3x plus 2, let it equal to 0 and solve for x. So this is my y, right? The f of x notation is y. Clear? Subtract 2 from both sides to isolate the negative 3x term first. And then we have negative 3 times x. How do we isolate the x when you have times negative 3? Divide by negative 3. Cancels. X equals positive 2/3. So x-intercept is 2/3, 0, or we can say it's at 2/3. One more page until break time. Special points, other than x-intercept, are also the turning points of the functions. Bit of description here. Some functions either increase or decrease, like for example, a linear function either has always an increasing trend or always a decreasing trend. But most of our functions beyond that, so degree 2, degree 3, 4, and 5, the ones we will discuss, won't be in this category. They will have interchangeably situations or portions of the graphs where they're going to be increasing and then they're going to switch over to a decreasing trend and further on. So for example, a parabola, an upside down parabola, will have a portion up to the vertex where it's going to be increased, and then after the vertex is going to decrease. So we can't say about these functions, oh, this function is a decreasing function, because it's not, okay? We have to describe increasing, decreasing on portions of the graph. So for example, the cubic function we will be discussing has this shape, some of them at least, and it will be increasing on the first part all the way to this point, this turning point, and then it's going to be decreasing all the way to this lower turning point, and then it's going to be increasing again. So how do we describe or define turning points? Is a point where the graph changes its direction from increasing to decreasing or vice versa. So in general, we always call them turning points. Sometimes we call them local minimum and local maximum. So this would be a local minimum, and this would be a local maximum. Some functions like parabolas, which are the graphs of quadratic functions, they have unique maximums and unique minimums, right? They're not local. They're actually, that is the highest value or the lowest value. And then you can just call them maximums or minimums. when we use the words maximum or minimum, it's a good thing to remember that they refer to the maximum y value of the function, the minimum y value of the function. Sometimes we use polynomial functions to describe prices. So for example, you may be getting a question when you use functions as application is, what is the maximum price you can charge for this t-shirt that you're producing based on an equation you're creating to maximize your earnings, right? So that maximum price will be the y coordinate of your functions. That's why it's good to remember that when we say maximum or minimum, that refers to y's, not x's, okay? Okay, so here's some examples. Here's a local minimum. So how do we say what the minimum is? We look at the left to see what that y value is for this point, right? So this y value is at -2. That's the minimum of the function, -2. It doesn't go anything lower than that. Here's an example with the maximum y value or maximum. You look for the point y value is 1. The maximum of the function is 1. Here's an example without the actual numbers because we don't know where it is, but here's a local maximum. This is actually a unique maximum if this function continues only downwards. So if we would know for sure that it doesn't come back up, then actually you can call that an actual maximum because it's highest value for your function. And local minimum because it's not the lowest value. You have other values that are lower than it, so local only. Example 4, same thing. Is this the maximum or a minimum of this parabola? Wait, it's a minimum at what? That's right. Because again, you're not taking the 1 there, that's the x coordinate, right? You're looking at the minimum y value. Minimum at 0. And for b, what's the maximum of this function? -1. Break time, 10 minutes. Because you're looking, so this is the point -3, -1. Maximum and minimums are the y values. So you always look to see how, like if you're looking at your graph, how high the graph can go. And high, low values refer to the vertical dimension of your graph, and that's your y coordinates. Left, right values are the x coordinates. Okay, so because we're looking at max, min, we're going for y's. Okay. So for us to be able to sketch higher degree polynomials, so we want to know some details from the equations of our polynomial functions that will give us information about the graph of these polynomial functions. So for that reason, we have these first few pages that relate the equations of the functions to their graphs. The first piece that will give you information about the graphs of the function will be the degree of the polynomial. The degree, if it's linear, cubic, and all that, it will tell you the shape of the graph. And you already know a couple of shapes. If it's linear or degree 1, the shape will be a line. That's right. If it's degree 2 or quadratic, the shape will be a parabola. A line, parabola. We don't know which direction though, we just know the shape, okay? Degree 3, I call it the snake. Thank you for remembering that. And I put it in quotation because it's not a mathematical term. It's just a term for you to remember the shape, okay? So snake means like this. 2 turning points, or sometimes none, but that's what it is. Degree 4. It's called a camel with 2 humps, or an M, or a W, whatever you want to call it. Degree 5, the slithering snake. Means you have more curves, hills, and valleys than the cubic one. So it'd be 1, 2, 3, 4, like that. Compared between, so this is the snake, but simpler looking slithering snake, you'll have more turning points in between, more hills and valleys. So shape. The next thing we're gonna know is how many of these hills and valleys we're gonna have. This is the third over here, but first is how many x-intercepts. Yes. How many x-intercepts we're gonna have? Up to n. So x-intercepts, recall, means the points that cross or touch your x-axis. Degree 1 can have up to 1. Degree 2 can have up to 2. Degree 3 can have up to 3. Up to 4, up to 5. You can see it's always going to be the same number as the degree of the function. Always up to. That means you can have that number or less, okay, but not more x-intercepts than the degree of your function. So a quadratic cannot have 3 x-intercepts. Can have 2, can have 1, can have none, but not more than the degree, not more than 2. We can also know from the degree of the function how many turning points. But not exactly, just up to what we can expect. It's going to be always 1 less than the degree of the function. Now let's take one example that you already know, the linear function. How many times it changes from a decreasing to an increasing or vice versa, a straight line? None, right? No, so you won't have any turning points, the straight line, none. Degree 2 has how many turning points? Quadratics, 1, right? Degree 3, it's gonna have either 0 or 2. It cannot have 1 because otherwise, if it only has 1, it doesn't come back up to make the shape that it is supposed to be. So either none like this, something like this for snake, like that, or 2, like that. So this one has 2, this one has none, because it doesn't change from increasing to decreasing. It just kind of goes to the right a little bit, you know, but not up, down. Degree 4 up to 3, degree 5 up to 4. 2. So when you're drawing your slithering snake, you can count, you know, a little bit. So you say, okay, 1, 2, 3, 4, and then up again. So 1, 2, 3, 4. But you can have slithering snake that have less than that, okay? Doesn't have to be 4 all the time. You can have slithering snake with only 3 turning points. Actually, 3 you can't, 2 turning points. So 0, 2, 4. Because it has to come back up. If you have 3, it'll be 1, 2, 3, and then you have to go down. It's not going to work out. Okay, so these endings have to be in those spots. We'll talk about the shapes a little bit later. We're gonna add a little bit more to the shapes a little bit later. So degree, 3 pieces of information: shape, what kind, how many x-intercepts, and how many turning points, up to for both of the last 2. The next thing that we're gonna be reading from the equation of the function is the constant term. And the constant term is gonna give us where the y-intercept is. So here's an example, 0.5 x minus 7. This is the free term, so I will know that the y-intercept is at -7. Remember, we can let x equal to 0 calculate it. It's gonna give us always a free term. Okay, and the last piece is gonna be the sign of the leading coefficient for a given polynomial function. This is gonna complete our idea of shape and direction. We call this shape and direction the end behavior of the graph. How the graph looks as your x goes really, really large and as your x grows really, or gets really small. So it will tell us the end behavior of our functions. Take for your notes or for memorizing degree 1 and degree 2 as your sample functions for their corresponding family of functions. All of the odd degree functions are in the same family for end behavior, and all of the even degrees are going to be the same family, meaning they're going to end in the same way. They're just looking like different functions because they have a different shape, right? So for degree 1, let's do here a couple of very simple x and y axes. You're going to have for a positive leading coefficient an increasing function. So it's going to start in quadrant 3 and it's going to end in quadrant 1. So this is going to be from here, quadrant 3, it's going to end in quadrant 1. That's how we can describe the ends, where it starts and where it ends. Now, if your leading coefficient is negative, then you're going to have a decreasing function. That means it's going to start in quadrant 2 and ends in quadrant 4. Since this is a sample for all of the odd degrees, the same start and end will be for all of the other functions, just the shape is different. And I'll show you in a second how that looks like. So if I have a cubic function with a positive leading coefficient, it would still start in quadrant 3 and in quadrant 1, but I will have the cubic function shape. For negative, still gonna start in quadrant 2 and in quadrant 4, just like the linear, but it's gonna have the cubic or the snake shape. Just like this one, the sample. Degree 5, another odd degree function. Again, same thing for positive leading coefficient. You're gonna have starting in quadrant 3, ending in quadrant 1, but then you're gonna have more turning points, right? For negative leading coefficient, starting in quadrant 2, ending in quadrant 4, slithering snake in between. It makes sense how you take this as your sample. So starting quadrant 3, quadrant 1, all of them will be exactly the same if they have a positive leading coefficient in the same family of functions. The functions with odd degree. You don't have to memorize anything, you just have to memorize the linear one. And then remember they have different shapes right? And then you're good to go. Now the sample for even degree will be degree 2, because everybody knows parabolas or should know. So a parabola that has a positive leading coefficient equation, it will be looking like a smiling shape like that. So this one starts in quadrant 2, ends in quadrant 1. And the negative leading coefficient equation for quadratic will be a frowning parabola. So starts quadrant 3, ends quadrant 4. I don't know how your brain works, but my brain works to memorize the shapes, orientations first, and then I look at it and then I describe the quadrants. I feel like it's way easier if you go that way, right? And then memorize where it starts and ends, and then try to go to the graph. And then for degree 4, degree 6, degree 8, it doesn't matter if it's even degree, they're all gonna fit in the same pattern for starting and ending, positive leading coefficient and negative leading coefficient. So for degree 4, we only do 1 because we only go up high as degree 5. So we don't want to include 6 and 8, but it will be the same. And then we have to have our ends quadrant 1 and quadrant 2. And then in between, we do our W. And negative is going to be with arrows degree 3, degree 4. And it's going to be a camel with 2 humps. Now the humps or the bottom parts of the W, they don't have to be even. It's nice when they're even, but sometimes you get something like that, okay? That's still a degree 4 function, okay? Sometimes even less than that, you can get something like that. A lot of different kind of shapes, you know, function. Any questions for these pages? For each of the equations below, give a rough sketch of an expected graph and identify the y-intercept. So we're going to justify our answers because we're still practicing and learning to remember where we took the information from. So to get a rough sketch of the graph or expected graph, that basically refers to the end behavior parts of your notes and behavior. Because to get the end behavior, you need the type of the function and the leading coefficient of that function. So for this first part, the type of the function, the polynomial kind, is degree 5 or quintic. And the second piece of information you need is the leading coefficient sign. So the leading coefficient is going to be the number that goes along with the highest exponent term. The leading coefficient is -1. So I just need the sign. So it's a negative leading coefficient. LC, leading coefficient in short. Because it's -1, it's right there, right? Make sense? So these two pieces of information will tell you what kind of sketch you should get. Quintic, odd degree, just like the linear functions. So remember, the negative leading coefficient for a linear function is going to be a decreasing line. And then if you imagine your line that's decreasing, starts in quadrant 2, ends in quadrant 4. But we have quintic. That means I have to have more turning points there. Like that. Make sense? rough sketch. You don't have to be exact. You just want to get an idea how or what kind of graph you're expecting to see once you start sketching these functions. The other part that they want is the y-intercept. All you need for the y-intercept is the free term. Which means the y-intercept is at 1 or the point 0, 1. Free term is positive 1. The y-intercept is at positive 1 or the point 0, 1. Sense? Questions? Another one. What kind of function is this one? Quartic or degree 4. What kind of leading coefficient does it have? Positive or negative? Negative. Quartics are the same ending or end behavior as your parabolas, right? So if it's negative for parabola, frowning parabola. So your two arrows for the ends are going to be downwards like that. Quadrant 3, quadrant 4, right? But it's quartic, so it has to look like an M. Like a camel with two humps, right? What's going to be the y-intercept? -2, because the free term is -2, therefore y-intercept is at -2, the point 0, -2. Now let's recognize some parts of equations by looking at the graphs. So for each of these given graphs, find the degree, sign of the leading coefficient, constant term, domain and range for the polynomial function. I'm going to take out that, the domain and range. We're going to leave that for later. So parabola in the first example, what kind of degree a parabola has? 2. How do I know? Because of the shape, right? If it's a parabola, that's the shape for degree 2 polynomial functions, right? So in brackets, that's how I know, because of the shape. Sign of the leading coefficient is negative. How do you know it's negative? That's right. So because it starts in quadrant 3, ends in quadrant 4, you can say because of the end behavior, in short, right? For this polynomial function. Constant term of the equation would be 2 plus 2, because the y-intercept is at 2. The second graph, what do you think the degree of this function is? I see signs. Anybody else? I see one more side. Okay. Yes, it's true. It's degree 3 because the shape is snake. And you can say because I only see 2 turning points if you want to be more accurate in your description and more mathematical, right? 2 turning points means it is a cubic function. Sign of the leading coefficient would be positive because it starts in quadrant 3 but ends in quadrant 1, just like a linear function in this, right? So it's an increasing trend, right? That's a positive leading coefficient. Oh, the quadrants, that's how they go. So it's your XY axes, and then you divide them into 4 equal sections, right? And this is quadrant 1 always, this is quadrant 2 always, quadrant 3, and quadrant 4. Okay? Just the location of the points. And the constant term of the cubic function would be -1, because we have, or we see the y-intercept of this function being at -1. Okay? Polynomial function. Here's all the steps that we have to know, or we have to memorize to get a pretty close enough sketch of a polynomial function. We will this time, when we're going to sketch, include y-intercept, x-intercept. We will know where it ends, where it starts, and then if we need extra points, we will have to include those extra points too. So I will take you through all these steps. There's no point of me talking about them because you'll have no idea what it means. You're just gonna sleep through it. Okay, so let's get straight to it, and I will number them as we go. So you can come back to this page and see what that first step represents, the second step, and so forth. Okay. Sketching polynomial functions. We are only going to focus on degree 3, 4, and 5 because in grade 9 you sketched, actually you graphed linear functions. In grade 10, actually grade 11, you sketched parabolas. So now those ones are in the past, and we will get to them when we do transformations in the second unit. But in this unit, I will only ask you to graph degree 3, 4, and 5. Clear? Okay. So sketch the following functions, justify each part of the graph. The first thing you gotta do in the first step when you're sketching is imagine the shape of the function, because there's so many different shapes. Degree 3 has a snake, degree 4 W or a camel, degree 4 the slithering snake. You want to visualize it before you get started with all the extra work that fills up the whole page, what graph you should get. So if you get something wrong in your calculations, you should come back to this first step and say, hey, am I getting the right thing? What did I do wrong here? Because you can get different shape in here in step 1 or in your final graph, right? So for getting the shape of your graph, you just need that end behavior reasoning. So we need the degree of the function, and we need the sign of the leading coefficient. So the degree of the function, when you have it like this in factored form, you got to look at the exponents of your brackets. So here you have x is to the 1, this bracket. This is x to the 2. So if you multiply those two leading terms, what are you getting? X to the what power? Yeah, 3, because you have a linear times a quadratic. It's going to give you a cubic, right? So degree 3. And now the leading coefficient. Here you have in front of x positive number. Here you have in front of x another positive number. What do you think you're gonna get in the end? A positive number, right? So you just have to reason it like that. We have a positive leading coefficient. Therefore, we can get a nice little sketch for our graph, an expected graph. It's a snake graph, increasing, right? Quadrant 3 to quadrant 1, or something like that. You don't have to write starts in quadrant. It just we're saying that so you know where it starts and where it ends. But once you look at it, you can see the quadrants yourself. Number 2 in the order of which you have to go through getting your sketch would be to factor your polynomial if it's not in factored form. But yours is already done, it's in factored form. That makes sense? So we can write here just for your notes that it's done, you don't have to do it. It's already factored. Number 3 is finding the x-intercepts. To get the x-intercept of the function, we have to let y equal 0, solve for the x's. For our functions, all you gotta do is rewrite your function as x minus 1 times x minus 3 squared equal to 0, so equal to 0, and then split and solve, right? The same way we've done in lesson 2, right? This is an equation that we've learned in lesson 2. Let's do that. In the first bracket, x minus 1 equals 0, x equals 1. Multiplicity of this one is 1, right? 1 is an odd number. Just write odd for now. And then the second bracket, x minus 3 equals 0, x equals 3. What's the multiplicity of this root? 2, right? From here, 2, because it's a squared bracket there. So 2, right there, even. Now, here's what we're gonna do when we're gonna sketch these x-intercepts in our graph. At the x-intercept that has odd multiplicity, we will cross over the x-axis. So we'll go beyond, just like a line crossing. When you have an odd crossing, when you have an even, you will be bouncing, which is touching and coming back down where you came from, or back up where you came from. So you will be touch or bouncing. Touch / bounce. So odds will cross, even will bounce. Yeah, I'll show you, okay? For now, just write so you have it in your notes, okay? But that's what it's gonna mean for us. That's why I told you last class, the multiplicity is important, okay? For this reason right here. Now let's go to the next number in our steps. So we found the x-intercepts. The next one is the y-intercept. For the y-intercept, we have to let x equals 0, calculate y. So y equals into the equation. Everywhere we see x, we replace it with 0. So 0 minus 1, 0 minus 3, everything squared. Now order of operations. What's 0 minus 1 in the first bracket? -1, right? 0 minus 1, -1. what's 0 minus 3? -3 squared. Now, in between -1 times -3 squared, which one you have to do first? The squaring, right? So -3 squared is going to give you +9. And then 9 times -1 is -9. So our y-intercept is at -9. Clear? Okay, now grab a ruler, a pencil. I usually do my graphs sort of on the right bottom side of my page. I want to sketch the Cartesian plane. That would be step 5, is pretty much putting on the Cartesian plane everything you have up to now, okay? So up to now, starting from the first step, is we have the shape and the end behavior. I wouldn't put the shape because I don't know yet how to unite everything, but I will put like the arrow here and an arrow there because I know that's what I should be ending with my graph. And you have to erase sometimes these arrows. That's why it's good to do the work in pencil. The next thing that I have is the x-intercepts. So I need some scales for my x's and for my y's. So I'm going to put x here, y here, label my axes. And then I'm looking at my x's, what kind I got is 1 and 3. So I have enough room to sketch, because if you get, for example, 10, right, you're going to choose a different scale than if you have this 1, 2, 3, and so forth. So I can say 1 is that big. And I'm going to put a dot like that to show that's where the x-intercept is, one of them. And I also have a 3 x-intercept there. And then we're moving down to the y-intercept. We have one at -9. So for the y scale, I'm not going to choose this big because then obviously I'm not going to have enough room to go to -9. So I can choose a different scale for the y. I'm going to choose that to be my 1. And then I can count 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's where the y-intercept is. So I put everything that I had. And then I also want to now discuss a little bit this crossing and touching, okay, because you were wondering about that. So if I come from down here, don't do anything, just to watch me. So I have to come from down here. So this arrow I'll have to remove. Somewhere down here, I have to cross here. I will go to 1, and it's telling me I have to cross it at 1. So that means this line of my graph will go over the x-axis, okay? And then I have to go up somewhere here, and I have to turn back to go to my next x-intercept. I have to turn somewhere here. And then when I get the second second x-intercept at 3, it tells me to bounce over there. So touch, right? So I only touch it and then come back where I came from. Make sense? So this one is crossing. This one, if I come from up here, it's going to bounce like that. Clear? And then it's just going to keep going. So I don't have any extra x-intercepts, so you don't want to include other crosses of x-axis or other touchings of x-axis. That's it, the ones you found. Now we have extra steps there. The extra step number 6 is to get some extra points to complete your graph, to support your work. Like notice how here when I said I'm going to go up high here, I don't know how high. So I would like to have maybe another point in between x1 and x3 to see how to turn over there, you know? It doesn't tell me the maximum there, the local maximum, but it will give me something extra. So I would do a little table of value there. And I would choose x equal 2 to get a point there in between. Make sense? So then plug it in. Plug 2 everywhere you see x in your original equation and calculate it. So 2 minus 1 is 1. 2 minus 3 is -1. Square it. -1 square is +1 times the 1. It's going to still give you 1. So the point is 2, 1. I'm going to name it my point A. So this is where 1 is. I'm going to put my point 2, 1 right there. A. Now, if you want more points, you can. I mean, here on the left-hand side, I'm pretty certain I'm on the right track. My graph is going in the direction that I thought it will from the first step. After the bouncing, I'm going where my arrow shows I should be going, so I'm confident. But if you're not confident, you take extra points, right? So if you want to see how the graph looks like over here, you can take a -5 and make sure your points are somewhere down here, right? And on the other side, if you don't know for sure if you got the right graph, you can take a 4 or a 5 and check to see if you're getting a y that's positive, that goes with the arrow over there in the top part of your quadrant 1, right? So I'm confident. Now, again, I get my pencil because I don't want to mess it up from the beginning. And I'm just drawing a rough sketch through my points, bouncing here. And you have to have a nice turn at your turning points. Imagine nice hills and valleys, lambs on the fields. Right? But what I'm saying here with hills and valleys or have nice turning points, I will show you what I don't want to see with your graphs. So there's something like that. When I'm confident I got the pretty good sketch of my graph, then I go over it with a highlighter. I cover all the little tiny mistakes with a highlighter. So it's clear what my nice shape looks like. And I am done. This is step 6. When I finalize 7, not step 6, step 6 is already done. When I finalize everything and I'm confident it's my final graph, check to see if you label your axes at this step. Make sure everything is included. Done. Now, what kind of shapes I don't want to see? So for something like this, that's a cubic function, I don't want to see that. It's not a shape of a polynomial function, okay? Because this one is a very sharp edge there. That doesn't happen with polynomial functions. They always turn smoothly, okay? So imagine parabolas at each of these sections. Parabola here, parabola there. They always have these nice hills and valleys like that, okay? No, sorry? Flowy, yeah. Smooth turning spots. Yeah, step 7 is once you have the extra points that you got here, now how can I unite these ones so I can get a nice graph, you know, and you use your pencil and then you get the graph, and once you're certain and you erase and it's looking nicely, then you just unite them all and you're done, okay? What time is it? Okay, we still have about 20 minutes, so I will do, should I do B or not? Yeah, let's do B as well. let's leave B just if you have extra time, because it's basically the same as the previous one. It's just gonna be a quintic function. I'm pretty sure I have a copy that I can give you. So it will be something like this. So that's gonna be the shape of this graph. Goes through the same steps as before, but it's the same already factored form. I'm not certain I have enough time for example 8, so I'll do this one first. Now, example 8 is sketching the graph of f of x, which is a polynomial function of degree 4, but this time it's not in factored form. So in step 2, you have to go through all of those skills we've learned in lesson 2 to get the factored form. Without the factored form, you can't find the x-intercept, so you can't go further, right? So you need to know those skills. Without it, you're lost. So sketch f of x, justify each part of the graph, meaning we have to justify for each step why we think that's the answer. Step 1. You need a shape that you're expecting for the graph. So you need degree and sign of the leading coefficient. Degree is 4. The sign is negative. Degree 4, negative leading coefficient is like a parabola downwards, but looking like. And remember, the humps, they don't have to be symmetrical. If they are, it looks a little bit nicer, but they don't have to. Next step is factoring. Let's factor. Starting with the free term that gives us where our choices are. Factors of 50. The 1, 2, 5. We go through the list. So do you want to use the method that uses factor theorem and then synthetic division, or do you want to use only synthetic division? Which one do you find easier? The first one, okay. So then we go through 1, find f of 1, negative 1 to 4, so plug in 1s everywhere you see x. And calculate and hope to get a 0, right? Negative 1 plus 9 minus 13 minus 45 plus 50. The positives are 59. The negatives are 58, 59. So equal to 0. X minus 1 is a factor, right? Synthetic division, negative 1, 9, 13, negative 45, 50. And we start. Negative 1, the first multiplication, add vertically, 8, and then 8, add vertically, 21. Why aren't we getting the same 0? It's negative 13, I copied it wrong. Yep. Then we have negative 13 plus 8, that's 5. With a negative. 1 times -5 is -5, so -50, we got it. Putting on the x's, no x, x squared, x cubed. That's what remains to be still factored, right? We can check again. 1, just to see. -1, 1 cubed plus 8, 1 squared minus 5 times 1 minus 50 equals -1 plus 8 minus 5 minus 50 does not equal 0, so 1 doesn't happen again. No more. We can check -1. -1 cubed plus 8 -1 squared minus 5 -1 minus 50. That's a -1, +1. If you multiply them, +8, +5, -50, not enough to neutralize the -50 there, so still not equal to 0, not a factor. Two, -1, 2 cubed plus 8, 2 squared minus 5 times 2 minus 50. -8, +32, -10, -50. Not enough. Too many negatives, so not equal to 0. The next in the list is -2. So -1, -2 cubed, 8 times -2 squared, -5, -2, -50. -8 times -1 is 8. Then we get positive 32 again, +10. I think this might be enough. So 40, 50 equals 0. X plus 2 is a factor. Once you find the factor, what do we do? Synthetic, -1, 8, -5, -50, -2 on the left. Drop the -1, get started. +2, that's 10. -20, that's -25. And then +50, that's 0. No x squared. This is a quadratic, so we're going to use quadratic methods of factoring. So we have -x squared plus 10x minus 25 equals. Now you can definitely factor this one with a -1 in front using the longer version. I showed that at the beginning of class. Here's an easier way that I think is easier, and this is the one that I always use. I factor out the negative first. So if I put -1 in front, I will end up x squared in the bracket -10x and plus 25. So now inside this bracket, I have the easier quadratics that you can factor, the ones that get you to the factoring form in one step. Because I don't have now a number that's different than 1 in front of x squared there, right? So now I here in front of x squared is just 1. Clear? Okay. All I need is 2 factors of positive 25 that add up to negative 10. Negative 5 and negative 5, right? So the factorization would be with a negative in front, the negative 1 that I factored first, I would have 2 brackets like that with xx. And then the negative 5 and negative 5, right? Or negative squared, because there's 2 of them, right? You just group them together like that. Now, how does the factorization of f of x look like for step number 2? F of x equals to what? Let's put it all together. X minus 1, we found first. X plus 2, we found second. And then we found x minus 5 squared. But then I have that negative in front of it. A lot of people forget about this negative, so I'll put that in front there. Because I don't really need it except for the calculation of other points. Okay, but if you leave it out, you're gonna get wacky points. They're always opposite in sign, you know, so it will mess up your calculations. So that's good. I can use now my factorized form to find x-intercepts and discuss the way they behave, either crossing or touching or bouncing, depending on their multiplicity. So step number 3, x-intercepts. The first x-intercept is going to be x equal 1. Multiplicity is 1 odd. Therefore, we're going to cross. The second x-intercept is going to be at -2. Multiplicity is 1 from here, from the exponent of the bracket. It's an odd number, so it's going to be crossing. And the last x-intercept is going to be at 5. Multiplicity is 2, right, squared, okay, and that's an even number. And for these ones, we will be bouncing. Now, from my experience, the error from understanding at this spot is people think the odd or even refer to the actual x-intercept. Okay, the multiplicity comes from how many times that bracket happens. Okay, it's the squaring or this one here. Okay, how many times the factor happens. Right, that's where the number odd or even comes from. So a lot of the times here, for example, for 5, students will say it's odd because they say number 5 is odd. Okay, but that's not what it refers to. It refers to the bracket the 5 comes from, because that's when it's squared, right? And the number 2 is even. Okay, step 4 is the y-intercept. This one is easy for the given functions that are already in general form, because you just look for the free term. So what is the free term? 50. You don't have to calculate anything for this one. Positive 50. Because that's what is there, right? Plus 50. So you'll know where to sketch it. Step 5 is putting everything together. Do we have some room on the next page? No. So you might need to grab an extra piece of paper for this one. If you're like me, I kind of implement it a bit. I could probably do it here, but I don't want it to be too small for you. Okay, so if you're like me, grab a sheet of paper so you can attach it. And let's make a nice and big graph for it. XY axis. Our intercepts are 1, -2, and 5. So I have to fit 5 here. So I want to be careful not to make my dimension for X too big. So I can fit the 5 of them into my image of my graphical representation. So that's how big my 1 is. And I'm going to do 1, 2, 3, 4, 5. There's my 5. And I need at 1 as well. And I have 1 at -2. The end behavior we discussed in the first step. So our graph needs to start here somewhere in quadrant 3 and has to end in quadrant 4. And y-intercept is at 50, right? So now I can't really fit 50 here. I can say, okay, this is where 10 is, okay? And you can go by tens. You can choose your scale to be skipping 5. If even so, your number is still too high. When you get to, for example, 40, you can do this. You can zigzag it like that and say, okay, I skip a bunch of numbers here. I get to the 50 much faster, okay? Sometimes you see that in textbooks as a dotted line too. You can see that it's looking like this. Okay, that just means I'm skipping a bunch of them to get to the value that I need because I can't sketch it otherwise, okay? But for us, you can just put a zigzag. Okay, so having a scale of 10 would work for this question. So 10, 20, 30, 40, 50, right? Now bouncing and crossing. What happens at -2? Do we bounce or do we cross? Cross, right? So we're coming from down here, we're gonna cross, makes sense, because we have to go up to our y-intercept first, right? That's the next in line. Then this is definitely gonna have to cross for y-intercept. You don't have to discuss it. It's gonna have to cross over. And then you come to 1 here. Do we cross at 1 or do we bounce at 1? Cross again, we go downwards here in the negatives for y's, and then we don't know how low we get. We're gonna have to figure it out. And then we have to come back up to the next x-intercept. What happens at this one when you come back up? That's gonna bounce. And it makes sense because if you cross it, to come back to this arrow where you already put down that you have to end up with, you're gonna have to cross again, right? And if you cross again, you create an extra x-intercept that you don't have, okay? This one you already know, it has only 3 x-intercepts and that's it, okay? So careful with that. This so far is good. Now, all I need to do now is just complete the information I have for my graph with some extra points, okay? So some extra points. These ones depend on you. For me, I would choose the -1. You don't even have to, but actually I wouldn't even choose -1 because I know for sure I'll go here. I would choose maybe 1, 2, the 3 from here. And if I really want to make sure, I would choose something on the outside, okay? So let's just do 3. I think that's enough. 3. Now, if you're not confident on your factorization, you could just use the original equation. If you're confident you got the right factorization, you can plug into that. You know, it's really up to you. But just be careful. If you had a negative leading coefficient, don't forget that negative in front. Because if you forget it, then you're going to get a different calculation or calculated value, right? So this negative here, now if you plug in, if you leave it out, obviously it will give you an opposite number in sign. So for that reason, it's always safer to always go back to your original equation, right? So negative, plug in 3, and then to the 4, and we have +9 3 cubed minus 13 times 3 squared minus 45, 3 plus 50. And you calculate that and you're gonna get negative 40. You can sketch that in two. So 1, 2, 3, 4, negative 40 right there. And now I do my best to unite the points again with nice hills and valleys, no zigzagging, okay? So I would go from here, and I'm gonna choose to do the turning point here because it just makes sense to unite the next point. Again, if you want to make sure, you can always plug in -1 and you'll see what happens. And then another pointer, when you graph it, don't do this. So everybody pay attention, don't do this, okay? Just try to now go nicely downwards with a little bit of a slope, but not that kind of slope. Because it won't do that, your graph. It will continue to decrease, but in the same way. And then I'm erasing everything. And then going over it with my highlighter. You don't have to. I just like to make them look nice in the notes. There.
There, why don't you go up a little bit before?
It's a great question. If I would go from here like this straight, if I go like that, then I would kind of have to come backwards on myself to get to this point. So it's kind of like sloped on this side. It just makes more sense when you unite them to have more of a nicer hill like that. But if you're not certain how to unite them, just choose this -1 as your extra point. And then you'll notice that it's going to be higher up in terms of a point, okay? You'll see it when you unite it, like once you get some practice with these ones, how like the flow of the graphs, they always have to be a similar way. So you won't have something that goes like that and then going to the next point sideways and then like that, because then it's not a function anymore because it's not yeah. Yeah, it'll be exactly, yes. Yeah. You got it. Okay, so that's the final one, except for that one that was already in factored form. So for that one, I'm gonna show you the key once we take a short break. I'm gonna go in the room and get the key to the other binder. So let's take our break now, and then when you come back.